This video provides a quick summary of the Simplex method, which is an algorithm for acquiring optimal solutions to linear programs. Let's look at a simple linear program. The problem has two decision variables, x1 and x2, and the objective is to maximize c equal to x1 plus 2x2. The problem has three constraints that are color-coded red, blue, and green. The optimal solution to the problem is x1 equal to 8/3, x2 equal to 2, and the optimal objective value is 32/3. The problem can be illustrated graphically like this, where each of the colored lines corresponds to one of the constraints. The black arrows indicate where the feasible solutions are, and the entire feasible region is shown in gray. The optimal solution is indicated by the red square. The Simplex method is an iterative algorithm that initializes in one of the feasible corner points. For example, this indicated by the orange circle. It then jumps to a new feasible corner point like this, and it continues to do so until it reaches the optimal solution. In order to prepare the linear program for the Simplex method, we first have to modify it slightly. The first thing we do is we move the terms of the objective function from the right-hand side of the equality to the left-hand side. That gives us the negative coefficients if we had positive before, and vice versa. We also modify the constraints. What we do here is we introduce a slack variable on each of the constraints. So for the first constraint, x1 less than or equal to 6, we will now introduce this x3 variable. This then allows us to change the less than or equal to sign to an equality instead. We do the same for the following two constraints, introducing x4 and x5. We are now able to write up what is referred to as the Simplex tableau. We have the modified linear program on the left and the corresponding Simplex tableau on the right. The first row of the tableau corresponds to the coefficients of the objective function, and the remaining three rows correspond to the coefficients of the three constraints. Notice that some of the columns in the tableau have almost only zeros and a single one. Those columns correspond to the basis variables, meaning the variables that have non-zero values in the current solution, presented by this specific tableau. Due to the way we've constructed the modifications of the linear program, this is exactly the solution where the two original variables have a value of 0 and the three slack variables have non-zero values. You can read the values of the slack variables as such. So x3 has a value of 6, x4 has a value of 4, and x5 has a value of 24. So by going from the ones in these columns. This solution corresponds to the solution that we started with in the graphical representation earlier. So we can show it here that the corner point solution of x1 and x2 equal to 0, that is exactly this solution here. The way to tell if a solution is indeed feasible is by looking at the right-hand side of the constraints. Because all of these variables are positive, the solution is feasible. By looking at the coefficients of row 0 of the objective function, we can tell whether the solution is optimal. Since one or more of these coefficients are negative, the solution is indeed not optimal. We then have to perform what is referred to as a primal simplex iteration. And this is done by picking the variable with the most negative coefficient in row 0 of the Simplex tableau, in this case -2. That means we know that x2 is the variable entering basis. In order to determine the variable leaving basis, we have to look at the relation between the coefficients in this x2 column and the right-hand side of the constraints. Essentially what we're looking for is the constraint that is limiting this variable the most. Looking at the first row, we see that no matter how many times we take 0, we will never reach 6. The second row, we can take 1 4 times and then reach 4. And the third row, we can take 4 6 times before we reach 24. So the second constraint is the most limiting, meaning that the corresponding variable x4 is the leaving variable. It should be noted that the intuition behind this is that by increasing x2 and decreasing x4 to 0, we increase the total value of the objective function, which can hopefully easily be seen by looking at the illustration as well. Now that we have identified the variable entering basis as well as the variable leaving basis, we are ready to continue the primal simplex iteration. The next step is to get zeros in every cell of the x2 column, other than one of the cells, namely exactly the cell where the two red rectangles intersect. Here we want a 1. In this case, we already have a 1 in that cell, meaning that we can skip to the next step. If we did not have a 1, we would have to multiply that row with the appropriate coefficient in order to get a 1. But, as I said, because we already have a 1 in that cell, we can continue to the next step of the iteration, which is to get zeros in the other cells of the x2 column. We do that by adding the highlighted row to the other rows. So for example, we add the highlighted row to row 0 2 times in order to get the -2 to a 0. And we subtract it 4 times to the bottom row in order to get the 4 to a 0 as well. We have now changed the basis solution such that x2 is in basis and x4 is not. And the illustration is updated as well. This concludes the primal simplex iteration. However, looking at row 0, we can see that the solution is actually still not optimal, as we have a -1 underneath the x1 variable. Hence, we could do another primal simplex iteration, and then we would actually reach the optimal solution. We now have no negative coefficients in row 0, hence the solution must be optimal. As mentioned earlier, if one or more of the coefficients of the right-hand side of the constraints are negative, the current solution is infeasible. In that case, we can perform what is referred to as a dual simplex iteration in order to restore feasibility. We look for the most negative coefficient in the right-hand side, in this case -1. This gives us the variable exiting basis, in this case y4. We then look through the negative coefficients of that corresponding row and compare them to the coefficients of row 0. This works very similarly to a primal simplex iteration in that we look for the most restricted variable, in this case y3, as 8 divided by 3 is less than 6 divided by 1. This gives us the entering variable y3. We are now able to continue the dual simplex iteration. First, row 1 is divided by -3 to give us a 1 in the cell in the intersection of the two red rectangles. Next, we subtract this new row 8 times to row 0 in order to get a 0 in the cell in question. And finally, we do a similar approach for row 2. Looking at this tableau, none of the coefficients of row 0 are negative, and none of the coefficients of the right-hand side of the constraints are negative, meaning that the solution is not only feasible, but also optimal. In the special case where the coefficients of the row associated with the variable leaving basis are all non-negative, it actually means that the dual problem is unbounded and the primal problem infeasible, and in that case you cannot go any further with either the dual or the primal iterations.